So in this part of lecture 36, I want to just kind of work through an example of what it would mean at the point of view of a matrix to find the singular value decomposition. Okay, so for this particular example, you really want to think of this operator or this matrix A defining the operator that's in R2, where it takes x1, x2, and it maps it to 2x1 minus x2 and 2x1 plus 2x2. So this is, if you want to think about what we're doing here, is this is the operator that corresponds to this matrix. And what we want to do is we want to find the singular value decomposition of this operator, but we can do everything in terms of the associated matrix. And the reason I chose this matrix is because we actually did a lot of work in the last couple of lectures that was kind of planned by me, is that we can kind of reuse some of our work. And here is some of the work that we need. Okay, so last time we computed the A transpose A, which is just this matrix right here. And so you're definitely getting a symmetric matrix. And we have to find because it's symmetric, so by the spectral theorem, we can find a diagonalization, but it's not this matrix here that we're interested per se, it's the square root of the operator defined by this matrix. And remember, the way that you do this is you keep your two outside matrices the same, but then you take the square root of each diagonal entry. Okay, so there we go. This is the operator right here, and so that part is useful. So, and then you can see what the singular values are, right? So the singular values of this matrix A are the eigenvalues of this matrix right here, and so they are lambda equals 2 and lambda is equal to 3. Okay, so there we go. We got the singular values. Now moving on, the other thing that we're going to need is the polar decomposition of the matrix A, and we already cranked that out last class. That's this particular matrix right here, but that doesn't make sense because this isn't a proper matrix, so let me fix that. I didn't copy down my notes right, so I apologize. So this should be the matrix 0.8 minus 0.6, 0.6, and 0.8. So this is my matrix A written in this expression. Now this matrix right here, right, this is the matrix, this matrix here is the square root matrix. It's equal to this matrix up above, okay? Okay, got to keep going, okay? So I want to go back here, and really what we're going to do is just kind of follow the proof. Okay, so we have this guy, it's self-adjoint, so we have to find, by the spectral theorem, we have to find the orthonormal basis, right? So we need to find a basis of eigenvectors that's also orthonormal, okay, because we have the singular values here. So we need the EIs, right? So what we have is, from this matrix, we know that these two columns here correspond to eigenvectors of 2 and 3. And so they have to be linearly independent because they're coming from different eigenvalues. And so it's actually a basis for our vector space. And they're actually, if you stare at it for a second, they are orthogonal. They are orthogonal. If you take the regular dot product of this, you get 0, but not orthonormal. Right? They don't actually have the right norm. They don't have norm 1. But it's okay. You have the Gram-Schmidt process. You can turn this into an orthonormal basis. So we'll do that. This becomes, and check my notes, make sure I don't mess this up, 1 over the square root of 5 and minus 2 over the square root of 5. And then E2 is 2 over the square root of 5 and 1 over the square root of 5. Okay, so this is our first orthonormal basis, right? First orthonormal basis. Okay, and now that you have that, okay, okay, so let's go back to the proof just so you can see where we are, because we're just kind of following the proof. we have this operator. We found the orthonormal basis for those guys. We had the singular value, and now for any vector v, we can write it in terms of this expression right here. But really what we're interested in now to kind of finish up is we need the S and we need all of these SEIs, right? And then we would be done because SE1 up to SEN is equal to F1 through Fn. Okay, so this is where the polar decomposition comes in, right? Because this is the matrix S from the isometry. So let's put the pieces together. So our second orthonormal basis is given by S times E1 and S times E2. So let me write out that information for you. So it's in your notes. So this is 0.8, 0.6, and negative 0.6 and 0.8 times the first vector, 1 over root 5, and negative 2 over root 5. And this becomes the vector 10 over 5 times root 5, and this becomes 5 over 5 root 5. Okay, now I'm not doing this in my head. I calculated this all out using Octave, just and double checking myself. So if you don't see how I went from here to here, it's because I did it on paper beforehand. And so we compute this matrix. Oh, this should be 2 root 5. 2 root 5 and 1 root 5. And when this spits out, I will get 5 over 5 root 5, and over here I'll get 10 over 5 root 5. Okay, and if you stare at this for a second, right, you should get something that's orthonormal. It's pretty clear when you stare at this, when you apply the dot product, you get 0, so they are orthogonal. And you can check that the length or the norm of these vectors is 1. Okay, so putting everything together means that this, when you take A and multiply it by a vector V, what singular value decomposition tells me is that's the same thing as taking 2, take V with the dot product, or the inner product of 1 over root 5 and minus 2 root 5. Okay, and so here, this inner product is the normal dot product. So this is the normal dot product. And then I'm multiplying it by my second basis element, which is this guy, or this basis element, the F. Right, so there we go. So remember, this is a vector, this is a number, this is a number, and then I have 3v, the second basis element, and hopefully I left myself enough room here. It's going to be nip and tuck here, times the second vector right here, 5 over 5 root 5, and 10 over 5 root 5. Okay, so these are the coefficients, right? You can't see what I'm pointing at. This guy and this guy are the coefficients. This is my basis. So any vector v, I know I can send it over. I can quickly figure out where to get sent to in terms of this expression. Okay, so there's a lot going on here, but this is what the singular value decomposition is. And there's kind of a nice way to write this in terms of matrices. What you're doing is you're taking this matrix here and you're taking the basis of where you're kind of the F's, and they become your columns. Oops. Right, and you know, I encourage you to kind of like go hit Octave or MATLAB and try computing this and making sure that I'm right. Right, and let me explain, let me write it all out because there's a lot of things going on here. Okay, so I mean, I'm doing everything over the reals. There's similar things for the complex numbers, but notice here, here's our original matrix A, right? So this is our original matrix A. Here is a diagonal matrix with the the singular values. Here, the columns are F1 and F2. And this matrix here, you have that the columns are E1, E2. But you have to remember that you're taking the transpose. So what the singular value decomposition says is, okay, you can take this matrix, find its singular values, and on this side, the columns are going to be one orthonormal basis. On this side, the columns are going to be another orthonormal basis, but it's up to transpose. Okay, and we'll talk about a little bit what this kind of means in the last part. Okay, but this is an example of orthonormal. Okay, sorry, the singular value decomposition term. And if you took Math 2LA3, you probably actually were able to show that even though we're focusing on operators, you can actually do something for any matrix. It doesn't have to be square matrix, where one matrix is a one basis, another matrix is diagonal with singular values, and then you get another matrix corresponding to a different basis. Okay, but we're kind of doing everything just on the level of operators. Okay, so I hope this example kind of explained what we were doing. This right here would be the singular value decomposition of the operator T that we started up with over here. Okay, so we'll stop and I'll see you in the last part of our last lecture.